Okay, welcome to lab 4 of this course. In this lab, we're gonna primarily focus on a feature of the oscilloscope called the trigger or the triggering feature. So in this video, I'm gonna talk about these stuff. First, I'll talk about trigger and what hold off is. And we'll talk about XY modes. We'll discuss a few limitations of the oscilloscope and other equipment. And then I'll quickly go over the different tasks and highlight some of the um, key things to look out for. And some students have also showed interest in learning about how to make circuits with AD2 and the oscilloscopes and stuff. There was some confusion about channels and inputs, so I'm gonna talk about that a little bit. Okay, so in the lab manual, there's also another term discussed called the coupling. So this coupling is something that doesn't exist in AD2, but it is an important idea and an important feature to learn for benchtop equipment. So I would recommend that you go look at what coupling is on the lab manual and in the lecture videos to at least know what it is. Right? But it's not going to help you with the lab on AD2, so I'm not going to talk about that in this video. Okay. All right. So first of all, what is trigger? Okay. So trigger is an event that dictates when the oscilloscope should display its update. Update is its display. Okay. So we'll talk about that in detail, but why do we need trigger? And the answer is that in order to properly resolve a signal on the display, and secondly, it's also used to view some of the relevant instances of the signal. Right? So what do I mean by resolve a visual signal, and what do you mean by like update the display and so on and so forth? Let's talk about really briefly. Right? So we're looking at signals that come in at say um, kilohertz frequency. So there's like 1,000 cycles per second, right? And if you want to look at the sine wave, then you have to zoom in on a few milliseconds of that signal. But now the question is, which few milliseconds do you want to look at on the screen, right? The oscilloscope doesn't know that. So it can grab this frame, or it can grab this frame, or it can grab this frame. There's no telling which frame it's going to grab for you to look at, right? And if you don't give the oscilloscope any instructions or trigger events, then say first time it can grab this instance, right? And then you'll see this picture on the oscilloscope screen, right? Something like this. And then after a while, the oscilloscope decides to give you this picture instead, right? And then it'll write that on top of the existing picture, right? And that will look something like this. Whoops, nope. That's going to look something like this, right? And in the third instance, it can grab this instance of the signal, and then you get another picture here. Whoa. Yeah, and that could look something like this, right? So even if the oscilloscope is clearing the screen each time and giving you a new picture, it'll look like the signal is moving back and forth on the screen, right? If it keeps some of the older pictures, then you're gonna get a fuzz on the screen, and there's nothing you can't really tell what the signal is. You can't tell what the period is. You can't tell what the amplitude offset is, so on and so forth, right? So to be able to resolve the signal properly, you want to have a proper trigger setting. So for example, the most common trigger setting would be a level and an edge type, right? So for example, here I have set the trigger event to be some voltage with a rising edge. So now what the oscilloscope will do is it will only update the display when um, when it encounters this trigger event, right? And it will place it in the middle of the screen, that trigger event, right? So it'll get this picture, or it'll get this picture, or it'll get this picture, right? So then what happens is it will get this picture, and maybe this is the first one it will encounter. It'll put it over here. And then again, it will get a second trigger event. It will put it over here. Third trigger event, it will put it over here. And as you can see now, the signal is tracing on top of itself, and you can easily make out what the signal that you're measuring is. You can make measurements on it, amplitude, frequency, and what have you, right? So this is an example of how triggering helps you to resolve the signal on the display so that you can make proper measurements on it. Another use for trigger is to look at particular features of a signal. So for example, I have, let's say someone turns on the switch, then the voltage across the light bulbs goes from being 0 to some volts, right? So maybe you're interested in how the voltage changes when you turn on the switch, right? So from 0 to 5 volts, is it doing something like this? Is it doing something like this? Is it doing something weirder, right? So we want to be able to know that. But this happens in less than a microsecond, say, right? And if you just don't give the oscilloscope any trigger settings, then you'll be looking at a flat line, and then all of a sudden you'll see 12 volts, and you'll miss this entire transient altogether, right? So instead, if I set a trigger level to say somewhere here, right, then the oscilloscope is going to track the signal, and as soon as it crosses, notices this trigger event, it's going to place, it's going to update the display right here, right? And then maybe you'll see that the signal actually does something funky like this, right? And this is important information for you to have as an electrical engineer, is what the signal is doing during transitions. So that's another use of trigger. Okay, so in this lab, we're mostly going to focus on trying to resolve a periodic signal on the display. And this kind of use of trigger will be useful in later labs, I think lab 7 or lab 9. Okay, now what is trigger hold off? So trigger hold off is the amount of time the oscilloscope waits before looking for another trigger event, right? So here, as soon as it finds a trigger event, right, after say about 20 nanoseconds, it starts looking for another trigger event, right? And that 20 nanoseconds is what we call the hold off. Now you can make that longer, say maybe a 1 millisecond, then after finding one trigger event, it's going to ignore any of the trigger event for 1 millisecond. And after that, it's going to start looking for another trigger event, right? So you might skip a few trigger events if you have a longer hold off. And that's useful sometimes for, say, signals that have a faster waveform superimposed on a slower waveform, like this example from your lab manual, right? So here, if you see on this trigger level T, you have several trigger events within a period, right? So if I were to just set this trigger level and a rising edge type trigger, then you'll see that all three of these events would trigger the oscilloscope to update the display. But as you can see, the signal is not symmetric about these points, right? So it doesn't look the same from this as a center point and this as a center point. And so you'll see some jitter on your screen. Instead, if you have some knowledge of the signal, then what you can do is you can use hold off and tell the oscilloscope to say, don't trigger on any event for 1 millisecond after you've found a trigger, right? So it might trigger on this one, and then it doesn't look, it will ignore the trigger events for 1 millisecond, and the next trigger event it finds is the periodic couple of the first one, right? So it could have found this trigger event at first, but still it was going to ignore, and then it's going to ignore some of the trigger events here, and it's going to find this one, right? So, but this trigger, this hold off has to be set with some knowledge of the signal. Otherwise, otherwise you can still have multiple trigger events that are not aligned with each other happening. Okay, so trigger types, there can be different trigger types. Most common one is, like I said, edge and level control. So rising or falling edge at a certain voltage level. You can have pulse width triggers or edge after edge trigger and several other different types of triggering. You look at the manual for the oscilloscope to find out what the different types of triggers. But trigger modes, there are two trigger modes. One is the auto mode and one is the normal mode, right? So the difference in these lies in the behavior when a trigger event is not found, right? So the difference is that in auto mode, if a trigger event is not found for a certain period of time, then the oscilloscope behaves as if there is no trigger setting at all, and it starts to refresh the display whenever it wants, right? If there's no trigger event and your oscilloscope is set to auto trigger mode, then it's gonna start triggering automatically to different to not the trigger settings that you set, right? But in the normal mode, if it does not encounter any trigger event, then it will just hold the last picture that was in there, right? So it will not update the screen until and unless it finds a trigger event. Okay, so that's the difference, and you will, if you're doing the pre-lab, then you'll explore the effect of that a little bit on the AD2. Unfortunately, trigger is something that it just does not exist in simulation. So you can't learn about trigger by doing simulation. Folks doing the LT-SPICE version of the lab, I would just pay attention to the lecture videos and read about it in the lab manual to a greater extent to learn about it more, right? So in lab 3, next topic is XY mode. And in lab 3, we sort of just talked about the different modes of the oscilloscope, right? The roll mode and the normal mode. And this is the third type of mode on the oscilloscope, right? How XY mode differs from the normal and roll mode is that in both of those modes, you have a voltage versus time graph being plotted. But in an XY mode, you have a voltage versus voltage plot, okay? So there's no time variable on this plot, right? So this type of XY mode is used to look at, say, the phase relations between two signals, okay? So for example, if you have two sine waves of the same frequency, and they're also perfectly phase aligned like this, right? So then what happens is when the first signal is 0, the second signal is also 0, and they're equal to each other throughout, right? So you'll see sort of a straight line when they're all aligned. but say you have two signals of the same frequency and they're anti-aligned like this. When one is increasing, the other is decreasing, then what you'll see is that, I'll say, when the first signal V1 is increasing, V2 is decreasing, right? So you'll traverse this negative path and then up again. So something like this. And there's and then next is, say, if you have the signals, say 45 degrees offset, something like this. So then what happens is when V1 is 0, V2 is negative, right? And slowly V1 increasing, V2 also increases. But when V1 gets to its max, V2 is now at 0. And then again, it does its dynamics, and you'll see sort of a circular looking graph, right? So depending on the different phase relations between the two signals, you'll see a perfectly aligned signal, anti-aligned signal, offset signal, or 45 degrees or 90 degrees offset signal, and so on and so forth. And by the shape of the XY plot, you can infer the phase relations, right? And say if the two signals were or not at the same frequency, then their phase relations will constantly change, right? And in that case, you will just see this plot changing over time. It will become something else, and then it will change, and so on and so forth, right? So because the phase relations is changing, the shape of the XY plot will also continuously change. But the key thing to keep in mind is that an XY plot is a plot that has two voltage axes, and you're plotting two signals on the same plot with no time variable. Okay, so so far we've discussed oscilloscope as this amazing instrument that can capture signals at kilohertz and hundreds of kilohertz of frequency, so thousands and thousands of cycles per second. But unfortunately, these amazing instruments also have limits, okay? You can have different kinds of limits. So like voltage limits, right? Current limits sort of don't apply to oscilloscopes, but definitely your power supply units and your wave gens have current limits. So how much current can it provide? We can also think in terms of the current limits, right? Sorry, power limits. So you can, so if there's a power limit and you have a very high voltage, then you're going to limit how much current you can provide. Conversely, if you have a very small resistor attached to the output, then it's going to draw a lot of current. And so there's only a certain amount of voltage that you can provide across it, right? So these are different limits. But in this lab particularly, we'll be focusing on the frequency limit of your oscilloscopes and your wave gen. So that will be in task 3. Okay, and I'll talk about that task in just a bit. Okay, so talking about the tasks, so starting from the pre-lab, the first is a few questions that you can answer. You're going to make some sketches and answer a few questions based on the lecture videos. And the next pre-lab task for the ones doing it on AD2, you're going to explore, like I said, the auto and the normal mode, and sort of notice the difference of how things change when you set it to auto mode versus normal mode, right? So in one of these cases, in both of these auto mode and normal mode cases, you'll explore two things. First, when there is a trigger event, and second, when there isn't, right? And so you'll sort of look at the behavior of the oscilloscope in those two settings in both the auto and normal mode, right? Okay, so that's the pre-lab. Task 1 of the AD2 task, you're looking at capturing and triggering off of synchronous and asynchronous signals. So synchronous means they're synchronized with each other, but in more mathematical terms, their periods have some common least common multiple. or a common denominator. Their periods have some kind of common denominator, so that when you can find some period of time after which the entire two signals will repeat itself, right? So for example, if you have a 2 hertz and a 3 hertz, this repeats every 2 seconds. This repeats, sorry, this you get, let me rethink that. So if you have a 2 hertz and a 4 hertz, so this repeats every half a second, this repeats every quarter of a second, right? But that means that every half a second, the 4 hertz signal is also back to its original phase. So we say that the 2 hertz and 4 hertz are synchronous signals, right? With synchronous signals, what happens is if you trigger on the faster waveform, then your slower waveform is automatically also triggered. But if you trigger on the slower waveform, then the faster waveform can still have a little bit of jitter, but you'll explore that, right? If you have, say, an asynchronous signal, like the 100K and the 100K 0.1 hertz, then things change a little bit, and you look at how that changes your oscilloscope display, both in the time domain and on the XY plot, right? So in task 2, we're gonna again explore how to use the trigger function to, along with the hold off, to trigger on a periodic signal that's a little more complicated than the sine wave, right? So a pseudo random bit sequence is a random bit of sequence, but it's pseudo because after a certain long period of time, it repeats itself, right? So it's not exactly random. The pseudo random bit sequence that you've been given has a period of 10 milliseconds. So for the first 10 milliseconds, it's a completely random set of bits, but after that, it's going to repeat itself, right? So you're going to try to trigger on this signal at first, but what you'll see is that the signal will be jittering all over the screen because you'll find multiple trigger events. But once you set the hold off to something just less than the period, then you should see that the signal is more steady on the screen. Another way to trigger on something like the PRBS is also to use a sync signal. This is a signal that most function generators or wave generators will produce. And the idea is that this sync signal is synchronized, right? The same synchronized or synchronous to all of the outputs, all of the signals that are being output by that wave gen. And so once you trigger onto the sync signal, you automatically trigger onto all of the signal that's being provided by the wave gen. Okay, so to sort of emulate that, what we've done is we've put a sync signal like signal on pin D1, and the PRBS comes out on D2, D0. So at first you only want to connect this up to your oscilloscope channels and try and trigger by using hold off. And in the fourth step, you're going to use the output on pin D2 to connect up to channel 2 and trigger off of that sync signal instead, right? So where do you find the pseudo-random bit sequence? So what you have to do is go into the course website and just download this file and run it with your Digilent waveforms software. Okay, and that will just open up this patterns and run it and give you all of the signals that's necessary on the appropriate pins. Okay. Now task 3, like I promised, has to do with the frequency limits. So you're going to generate a signal that is very fast. In fact, the fastest that you can generate with the function generator. So for the AD2, I believe it is 10 megahertz. But you can check that. And you're going to try and view that on your oscilloscope. And if it isn't clear from the topic that this task is exploring, then I'll tell you that what you see captured on the oscilloscope may not be what you intended as to generate, or maybe it's generating that, but it can't, the oscilloscope can't capture it properly, or it could be that the wavegen itself cannot generate the fast signal properly, or it can be that it got lost in translation when you connected it. So there are several different possibilities that it could be, and your fifth task is to sort of just ponder on what could be the reasons for your square wave to not look like a square wave. Okay. So for folks that do not have an AD2, triggering is something you cannot do on LT-Spice. There's no simulation version of triggering. So the tasks here for this lab will not involve any triggering. But what you can do is you can look at the XY plot for two signals, right? And that at least sort of covers what people are doing in the first task of the AD2 version. The second task is to keep you a little bit busy, and it explores the idea of superposition. If you'd like to learn a little bit more about superposition, look at the Lab 5 in Lab 5 theory section in your lab manual, or also the Lab 5 lecture videos. That'll give you a little bit of idea of what superposition is, and do this task. Okay, so so you don't have to apply any superposition principles to be able to do this lab. You just there's some questions about what you expect. Just tell me what you expect in terms of your intuition about the circuit, right? If you know what superposition is great, and just explain your expectation in terms of that superposition principle. Okay. All right, but other than that, I think folks without the AD2, I would again implore you to focus on the lecture videos and the demonstrations that are shown in the lecture videos to get a better understanding of what this trigger is all about. Okay, because it is quite an important topic. Okay, so now quickly, I'm going to talk about AD2, the oscilloscope, and how to connect it. So first of all, AD2 again is not one instrument, but it has multiple instruments packaged into one device. And the different instruments can be accessed through different pins of the AD2, right? So the wavegen can be accessed through W1, waveform 1, and W2, waveform 2, two different waveform generators. And the oscilloscope, these are called the outputs of the wavegen, okay? Because this is what generates it, and it makes it available, so it gives it out, right? So it's an output. Oscilloscope has 4 sets of pins associated with it, and these are the inputs to the oscilloscope because it's measuring, right? And there's 2 sets of plus and minus pins, 1 plus 1 minus and 2 plus 2 minus. Each set is a channel, right? Think of it as a voltmeter, right? Your voltmeter has 2 pins, right? 2 wires. So these 2 form 1 voltmeter. These 2 form another voltmeter, right? And if you want to measure the voltage across a resistor, you have to connect these 2 pins across the resistor, okay? And yeah, so that's how it works. Okay, so a quick example of how to connect things up, right? So here you have a voltage divider with 2 series resistors. I'm applying a V in, a sinusoidal V in across the the series combination of the two resistors, right? So first of all, to build this circuit, what I need to do is connect waveforms 1, right? That's what's generating this. So W1 to the top resistor, and then the top resistor connects to the second resistor, and second resistor connects back to ground. Okay, and this ground you see here in the circuit that it's connected to the wave gen, and internally it's also connected to the wave gen on the AD2, right? So this ground is what we call common ground. Okay, and so now the circuit is complete. Next, the task is to measure the input voltage on channel 1 and measure the output voltage on channel 2, right? So how do you do that? So first of all, if you want to measure the input voltage on channel 1, you want to measure over here, right? So this is the input voltage, V in, which is, you want to connect the 1 plus to here and 1 minus to ground, okay? And then if you want to measure V out on channel 2, V out is over here, right? Across R2. So what you'll do is you want to connect 2 plus to here and 2 minus again to ground. Okay, so ground is, you might have another ground here, so connect it up here. Right? So that's how you want to connect up the circuit to measure the voltages on this circuit. Okay, so hopefully that makes things a little bit clear about how to use the oscilloscope channels, pins, inputs to measure different voltages on your circuits. One thing to keep in mind is oscilloscope does not measure current. So there's never going to be a need for you to put these two, put the oscilloscope channel in series with any component, right? So if you do that, you run the risk of damaging the input ports of the oscilloscope. So always put it in parallel to whatever device you're trying to measure the voltage across of. Okay, so with that, I'm gonna stop the